we're going to quickly go over what we did. So what I'm going to do is open that discussion in this one. Oh no, this one in student mode, and then I will submit. I'm gonna submit the same, guys, but I'll explain few things. Okay, so let me go back to right. So this is my work, so I'm gonna submit the same, right? This one. Okay. So remember, so we are talking about abstraction in in English. Okay. So um, perspective is important, right? So this is in the sense that the user's perspective, right? So you are using, let's say that in this example, making a bread, you are using a bread machine to make a bread. So you are the user. Okay. So if I am the user, I don't. I mean, as long as I get a good bread, the bread that I want, based on the input, I'm fine, right? So I don't need to know how the heating works, how the yeast works with the thing, and then how long it take, like those things, right? So that's too many detail, right? So we should not expect to know all the details, right, to get something done, because it's you can think of it, it may be hard to comprehend, right? So having expected from you to rely on that much of information, right? So that's why one of the other name we use for abstraction is information hiding, right? So it goes everywhere, right? So for example, it's not just, so this is a function or a task, so that means they involve verbs, right? But it also goes with names as well, right? So for example, if I say like this screen, right? So if I say a screen, you guys know that it's a screen from the looks of it, right? Right. So and then we basically get together some features and then give it a name. Okay, this is a screen. And then by learning and then things, we know that it's actually a screen, so we basically don't use this square thing and that lights up when power. We don't have to say that, so we say the screen, right? Same for the chair, right? So that the example I took last day, right? So basically, having to comprehend too many details, it's a it's a hassle. So to avoid that, so basically we give it a name and then use that name. So it's the definition, right? So but here's a big thing here, right? So um, if you are the engineer who designed the bread machine, then you need to know everything. Okay, right? So that's what we call domain knowledge. Okay, so in this class we will be writing code, so we need to know the domain knowledge as well. Okay, so when you write, let's say, a function later on in the class, like using code Python, you need to, you are basically not the user, you are the engineer who write that code. So you need to know how to code. Not only that, you need to also have the domain knowledge of the problem you are going to solve. Okay, but we, when we do that, we think about the user, right? So the lay person, that who is going to use the code, right? So for that lay person, the way the code written, it's not important, right? Or even the way the problem solved is not important. So as long as it solves the problem and you get the output you want, you're fine. Okay, so that's abstraction. Okay, so I'm gonna reply to this one as a student. Okay, so I saw few of you guys still haven't like embed inserted it properly, right? So um, so let's, this is me as a student, right? So you go over here, so reply. Okay, and then guys, um, please don't do this, right? So when you attach, right, just the file name is there, and then none of your classmates will open it. Okay, they will not do that. And even for me to grading, it's a hassle now, because I have to download your file and then open it, so it's not visible, right? So if you have an image in this class and then you need to submit the image, you always insert it. Okay, go over here, click on the image, upload image, and then right, so go over here and then select the image and insert. Do not attach, please. Then I would make a name to this so that it's accessible. So make, right, so and then we submit. Okay, so and attach, so sorry, insert, and then I basically reply. Okay, so that's my post. So please do not attach. Okay, so all right, any question before we proceed, guys? Yes.
Yeah, because I had sent that in last class as improperly. So
Yeah, you can. So here's how we do. Let's say you made a mistake. You go over here
yeah,
and then edit. Yeah.
cool.
So you can always do that.
And so, but we still get credit for that.
Yeah. You get full credit. Yeah. So that's
So
fine. I mean, as long as basically, so there are unlimited attempts, right? So if you don't get the full mark, read the feedback and then correct yourself. Okay. All right. Yeah. And yeah, I think that's yeah. Okay. I'm gonna. All right. So we're gonna go to SciBook. So I think we were over here. All right. So remember we were over here, right? So okay. So and then this we learned this. We broke down. Remember we took a number and then broke it down, right? So and then this is how we see how the formation of the like breakdown of the decimal number, right? So this is how we do it for binary. Okay, so each digit represent a level of significance and it increases from right to left by 1, right? So for example, so the binary number we are dealing with right now is 1101. So the rightmost digit is 1, it's actually 2 to the 0th position. So and likewise we go up towards left 1 by 1, right? And then so when we sum up those powers, like those sums, what do we get? Yeah, in what base? Base 10, right? So that's base 10, 13. All right. So if you want to convert 1101 in base 2 to decimal, I mean 1101 in binary to decimal, this is how you do it. Okay. Now remember this as a fact. This is how you convert binary number to decimal. Okay. All right. So let's go from there. So I'm gonna say one. This is 1000 now, and then these are these zeros important? No, right? It's like you write like you write me write like this, like um, let's say if I write 13, right? this is base 10, so I'm going to write it in small subscript base 10, right? It doesn't matter how many zeros you put to the front, right? So it's still 13, right? So that's that. Okay. So so this is these zeros are insignificant. Okay, and you can see that they are add nothing to, right, to the number, right? So so this is 8. So if I put one more, this is now 9. Likewise, right? Okay. So and then you can actually convert that way. So we can answer this. So let's quickly answer this one. Convert the decimal so not that one, sorry, let's answer this one. We're going to come back to this one later. So let's convert this one. Okay, so it's 100 1000. Okay, so I'm gonna set this. So 1000 1000, right? See that? So what's the answer? 136. All right, there you go. Okay, all right, so we're gonna go to the next one. This topic is really important. Entire previous class was spent over here, so I was thinking to finish the chapter, but no. And then same will be here, I believe. Okay, so all right, so um, so let's before getting into this one, I'm gonna start off with a workout. So we already learned how to convert binary to decimal, right? You saw it in the 2.8 section, right? All right, how do we convert decimal to binary is the question that we are going to just answer. Okay, how do we convert decimal to binary? Okay, all right, anyone has the answer? I want the name of the technique. Yes, you're right. Yeah, so we're gonna learn about the divisional one. So but it's yeah, it involved dividing, but I want the specific name. There's a specific name for that. It's also, yeah, it's factoring actually by 2, right? But that's a specific name for that. I'm yeah, I'm pretty sure you may have stumbled upon this in the past, but we're gonna learn it right now. Okay, so we call it, it's a division. There's an adjective in front. All right, so let's learn the technique, and then we can give it a name, right? Okay, so I'm gonna go over here. Okay, maybe I'm going to dump the whole thing, and then all right, okay, okay. So I'm gonna take the number. Let's take the number. Okay, let's take number 5. Okay, 5 in base 10. Okay. Oh, all right. So let me. All right. So 5 in base 10. So base 10. Okay, guys. No, this is not 500. This is not 510. Okay. So 5 in base 10. So when we are dealing with more than one bases, it's good to write the base as a subscript. Okay, so that's what I have done. So it's a subscript, same base 10. Okay, so what I want is, right, so I want, okay, so what is this in what? Base 2, right? Okay, so we're going to answer now this question. So we're going to use division. Okay, what number should I start dividing then? Yes, 2, right? Because it makes sense, right? So logically also it makes sense because we are going to convert decimal to base 10. We're going to convert decimal to binary. So that's 2. So we should be dividing by 2, right? Okay, so let's start doing that. Okay, so all right, so what's the answer here? How many 2's do we have for the 5? How many 2's in 5? 2, right? So we have 2 whole 2's in 5. So what's left? 1. So you're going to write 1 over here. So this is what left. So this many 2's we have in 5 that add up to 4, right? 2 times 2 is 4. And then the rest is 1, right? So this is the remainder part. This is how many 2's do we have in there. Okay, so we are not done yet. So we need to divide one more time, right? Okay, so we're going to divide one more time. Okay, and then we get 1, right? So oops, what's left? Yes, so we have 2 here. When I divide 2 by 2 we get 1, and what's left? Nothing means nothing means 0, right? Nothing means 0, right? So 0. Okay, all right, so we do this until we reach 0 at the bottom. Okay, so we are not there yet because we have 1 here, it's not 0. So we're going to divide one more time. 2. How many 2's in 1? 0. There's no 2's in 1, right? So it's 0 here. So then what's left? 1, right? Okay, that's it. So what is the way we divided? So it's division, but the way we actually repeatedly divide, right? So we call it repeated division. So that's the technique's name, repeated division technique, to convert between number system. They pretty much convert between convert decimal to whatever the base. In this case, base 2. So we're going to convert. We are converting base 10 to base 2. So so now it's good to identify the pattern. So I am dividing by what?
2.
Yeah, 2 is what here? The base I want, right? So you want the base 2 binary, and then you start dividing by 2. You want the base 8, then what do we start dividing by? 8. We want the base 16, the hex, which we're going to learn just now. We start dividing by 16. Okay, so the base we want, we start dividing by that one repeatedly until we reach 0 at the bottom. Okay, and then we write the remainder by the side. So now how do we get the binary number? Is we basically read from bottom to top. Okay, all right, all right. So the answer is then this. I'm going to erase this one, and 101 is the answer. Okay, so it's really sensitive.
So that 1 at the bottom represents the 4 place? Because I would have thought that it was the 2 divided by 2 gets you a 1.
Mm-hmm.
So that represents the number 4, and then you have 0 for 2, and then on the bottom you have 1 for 1.
So basically, we have to divide until we reach 0 all the way to the bottom. Okay, that's 1, and then we write the remainders by the side, and then why we read from bottom to top is because we write numbers from left to right, right? I mean, in when we write decimal number, we write it from left to right, right? So that's why we write it from bottom to top. Okay, so and then we yeah.
So that 1 at the bottom is the first number that I'm writing.
Yes, and then yep,
That's in the fours place, and then the next. The
you're
zero
right.
is in the two place, and that one at the top is
Yep.
in the one.
Yeah, you're right. You're right. Yep. Okay. So zeroth, yeah, fourth place. You're right. Yep.
Okay.
Yep. All right. So are we okay with this technique now? So we can go a little bit higher number as well, right? So let's go for 16. Well, let's go for 15. Okay. So I'm gonna take 15 base 10. Okay. So I want whatever the number in base 2. Okay. So I want this in base 2. So this is perfectly equal. So that's why the three lines there. Okay. So it's equal but perfectly equal. All right. So we're going to divide by 2, right? So we call this repeated division. So we get what here? 7 and 1. So one more time, and 3 and 1, right? So keep going, 1 and 1, right? And then we get over here 2 and 0 and 1. So we read from this end to this end. So we get actually this one is actually 1 1 1 1 2. Okay, base 2. Okay. And we already know from converting that to the decimal, right? So it's basically to be doing it one more time, right? So basically we write it like this: 1 1 1 1, right? So this is 2 to the 0th position, so 1 time 2 to the 0 plus, right? And then 1 times 2 to the 1 plus, 1 times 2 to the 2 plus, 1 times 2 to the 3. So this is actually 8, right? So it's 8 plus 4 plus 1 plus 1, right? This is actually 15. Okay. So we got the answer over there, right? So this see that's 15. Okay. All right. So that's clear now. All right. So so let's say so let's can actually start off with the yeah. All right. So now if I want octal number, okay, that's base 8. So what are the digits in octal system?
0, 8, 16.
Now let me take it back. Base 8. So we call it octal system. Oct means 8, right? So what are the digits?
0, 1, 2, 3, 4, 5, 6, 7, 8, 8.
Nope. Anyone? Well, we learned that, right? So when you take a number system base, the last digit of that system is 1 less than the base, right? So the take decimal system base 10. What is the last digit in the system? 9, right? 1 less than 10. So that's the pattern. So if it is 8, then the last digit of the base 8 system is 7. So we have 0 to 7 digits. Okay. So imagine I am converting 15 to base 8, then which number should I start dividing from? 8. 8. Because it's the base. We take the base and then start dividing from. See that base is we are converting to binary. So base 2. So we keep on dividing by base 2, right? So we take the base and then we use that to convert. So now, so let's convert, okay? So, and you can see that you can get pretty much convert any decimal number to any base you want, right? There's no limit to that. I mean, you can do that. Even for decimals, you can do so. But why do that, right? But in computer science, we are only talking about the important one for us, really important base 2, because that's the language, zeros and ones the computer understand. And then base 16 and base 8 usage, the octal usage is diminishing right now, but we are actually teaching it anyway. Okay, so base 2 decimal, base 2 octal, base 8 hexadecimal, base 16. Okay, so let's take base 16. So I'm going to convert 31. Okay, so let's take 31 base 10. All right, what I want is base 16. All right, what do we do? Yeah, start dividing by 31 by 16. All right, so all right, so how many 16 do we have in 31? 1. What's left? 15. And then one more time, right? 16. We have 0 now, because we remember pattern is we keep dividing until we reach 0 at the bottom. Okay, so that's what you, so those are facts that you guys should remember. Okay, so now what's left is 1. Okay, so now we kind of hit a snag. Okay, so well, let's try writing this now, right? Because that's what we did, right, from bottom to top, right? So this equals 115, right? So 1 is here, this one, and then 15, right? What's left is 15 and 16. This is problematic. Why? Yeah, I mean, here's the problem, right? These all numbers we get over here, the residuals, like like right here, these numbers, they are digit in the respective number system, right? We saw 1 zeros in the when we convert 2, right? Right? So they're supposed to be digits. So then that whole 15 supposed to be a single digit, but it's not appearing as a single digit, right? There are two symbols there. That's a problem, right? So the bottom line is basically this. So in decimal system, we go from 0 to 9, and there are 10 unique symbols, each one symbol, right? But when we go to other bases like base 16, right? So we need more symbols. Like 1 0 is also should be represented by single symbol, but we don't have unique symbols there, right? Because the numeric system developed before we come up with decimal system, right? So sorry, hexadecimal system, right? It developed in the 21st century pretty much, right? So then basically we have to come up with the protocol or convention. What is the convention? We use letters of the alphabet, English alphabet. Okay, so let's go to that one. All right, here you go. Okay, all right. So we have decimal, right? So then we have after 9, we cannot use 10, right? Because if we try to use 10, it's two symbols, right? That's problematic. That's confusing. Okay, so instead of that 1 0 2 symbol, we take A, and then 1 1 is B likewise. Okay, so this is now basically you can write this, instead of this 15, you're gonna write what then? F. Yeah, all right, so you're gonna write this as F. So this is actually then 1, this is actually not this, it's actually 1F. Okay, base 16. Did you all understand my point? Right, because so these are all should be digits in the expected number system, right? So that means they are supposed to be single symbol, not two like 1 5, right? So instead of 1 5 writing like 1 5, we actually write a single symbol F, and that's the standard. All right, question? Okay.
So it wouldn't be written out in the, I don't even know if this is right, in the binary form of F. We can't write one and then look at what F is and start and then write zero, one, zero.
So yeah, I mean you're right, but we are here we are converting decimal to hexadecimal. So we're gonna get into binary later. Okay. All right. Okay. So all right. Yes.
So this is saying 1 plus F, 1 being 1 and F being 15.
Don't take plus. No, it's the breakdown is going to be the powers 16 to the 0 plus 16 to the 1 likewise, right? So it's basically the way or the order we write, right? 1 comes first and then write F, not 15. Okay. All right. All right. So so this is basically, so this we now know how to convert from decimal to hexadecimal, and then let's try to convert hexadecimal to real quick to decimal. So basically we should get 31, right? So let's see how it works, right? So F means, so basically we basically take like this, right? So it's 1 times 16 to the power 1 plus, right? F times, right? 16 to the power 0. But now we have to use the actual book value of it. What is the book value of F? 15. So instead of 15 over here, so we're gonna actually write instead of F here, we're gonna write 15. Okay, so this is 16 plus 15. So 16 to the 0 is 1. So this is 15 equals 31. So we got the answer back, right? 10. Okay, so this is how you convert back. Okay. Any question on this one? So things to if you want to remember this as a pattern, here's how, right? So take the base that you want to get and you start repeatedly dividing by that base. Do it until you reach 0, and at the same time write the residual. If there's no residual, that means 0. Okay, and then read from bottom up and then write from left to right the resulting answer. Okay. All right. So yeah. So let's yeah, I think so we can now answer some of the questions over here. All right. Yeah. Oh well. Yeah. So let's do one more exercise. Okay, guys. So we did this one, right? Okay. Let me ask this question. Take hexadecimal system. My question is, what is the last digit? F in decimal 15, right? Right, in decimal it's 15. Okay, and then what do we see over there? So 15 in decimal, you need 4 binary bits to represent 15 in decimal, right? Right. So that means F in hexadecimal, you require 4 binary bits to represent. Am I right? Right. Okay. So my question is, to represent a single hexadecimal digit, how many binary bits do we require? Yes, why 4?
Because you need 4 to represent the number 16.
Is it 16 or 15?
The 16 would be the
Yeah.
16 is 1, 0, 0, 0, 0.
Yeah. So see the answer is over there, right? So here's again here's how you connect the dot, right? The last digit of the hex system is 15, okay, which is F, okay, and we require 4 binary bits to represent that. What is the first digit in hex system? 0, right? So to represent 0, you require like 4 zeros in binary, right? So since we require 4 digits, 4 binary digits to represent the last digit in hex system, so that means we should take 4 binary bits to represent a single hexadecimal bit, hexadecimal digit, okay, got it? And that's why they have given this table, okay, see that we have to not just 0 binary bit. For 0 in hex we have 4 zeros. Why? Because for representing 15 we need 4 bits in binary, so we better keep that 4 as a unique value all the way from 0 to 15. Got my point? Right? So to represent binary in hex, so basically you need groups of 4, and then here's how you do it actually, right? Just play this animation so we actually grasp that, okay, all right. So that's in these are binary values, right? So we don't see yet what are those, and then these what are those, right? And basically that's in, so if you take right, and what do we do then, right? So here's the mechanism. That's a 8-bit binary number. See that we have 8 bits there, right, if you count. So starting from the rightmost bit, we start grouping 4 at a time and go left, right? So the first 4 group is, now we know the value is 7 in hex, right? So 0 1 1 1 is actually 7 in hex, right? So we write 7, and then we go to the next group of 4, and then 1 1 0 0. From that table we know that actually it's true, it's C, right? So we write C. So the conversion is C7, okay, in hex. So this is one way of converting decimal to, sorry, binary to hex without going through math, because we're going to learn another technique later, okay. What time is it? Okay, we still have 10 minutes, okay, all right. So you don't have to remember this table. You can actually, if you know the pattern, you can create the table by yourself, okay. But given this table, you can pretty much convert between either way, like binary to hex or hex to binary, okay. So binary to hex, basically we group 4 at a time starting from left to right, right, and then based on that table we put values. To hex to go to binary, again we start from right to left and take but one binary, one hexadecimal digit, and then write the respective 4 binary bits, okay. So using this table, okay. So you can use this table easily to convert back and forth hexadecimal to this to binary and binary to hexadecimal, okay. But we're going to also learn a mathematical way to do that. Yes.
So basically, what you're saying is the reason why we need 4 bytes
Yep.
to represent a hex number is because the maximum number of
Yes.
requires 4 bytes.
Yes.
So if we were using a base
4 bits, not bytes. 4 bits. Yeah.
So
Okay.
if we were using, for example, base 5, we
Mhm.
would require 3
Mhm.
digits to represent a 5 base number.
So that you have to actually you are talking about base 5, right? 5 as a base. then when you actually convert that, so then the last digit is 4, right? So to represent 4 you need 3, right? So you can actually you can use groups of groups of 3. Yep. Yeah. Yes. You can try it out and create the table by yourself and then see if the numbers make sense.
Okay.
Yeah, it's good exercise. Yeah. Okay. All right. So let's okay, now so we learned so we can actually try real quick octal as well. Okay, so basically let's take number 8 um, in octal, sorry, 8 in decimal in 10, and then we want in base 8. Okay, so we start dividing by 8, right? So 1 and 0 and one more time and 0 and 1. So this is basically 1 0, but it's not decimal, guys, it's base 8. Okay, all right. Okay, so to convert from octal to decimal, we break it down, right? So 1 times 8 to the 1 plus 0 times 8 to the 0, right? It's just now 8. Okay, so all right, so let's quickly write that one as well. So it's a conversion back. It's 1 times 8 to the 1 plus 0 times the last digit right here. This one is 0, right? So we take that 0 times 8 to the 0. Okay, so this is 8 plus 0 because we have 0 over here, right? So the answer is 8 in base 10. Okay, all right. Okay, so any question? Okay, so yes.
So when do you like? So for example, as example, where it was like 1 to 15,
Mm-hmm.
then that was like a negative. So that goes into hex, or
Can you go again? 1 to
so for example, like it was 1 minus 15,
sorry.
right?
Oh, it's not minus.
Oh, it's just
It's not minus.
mm.
Sorry, guys. This is not minus sign. Okay. So this is what basically the notational. I am writing the residual. This is not minus sign. So what I am saying over here is like for 8, when I divide by 8, I have one whole 8 in there, and then what's left is 0, nothing, right? 0.
Right.
So it's notational only.
Not
Okay.
going to page.
Yeah, it's only notational. Please, it's not 1 minus 0.
Okay.
Okay. All right. So all right. Let's go. I think we can now answer some of these. Okay. All right. So let's take the last one. What's the answer? Number 7, guys. All right. So we're gonna start grouping from here, and then take one this 4, right? Then this 4 likewise. We go towards left and then group, right? So and then we read it from there, right? So
One is zero.
yeah, 1 F0 is the answer. Okay. All right. And then we have to make sure that we also write in that order. So we are going right to left, right? So we should be writing also right to left. Kind of odd to write that way, right? Because we used to write left to right, right? So you can do the mental model, and then finally write the whole answer from left to right as well. Okay. All right. Okay. So let's do this one. Now I think it can convert binary to hex. Okay, let's do this one. What's the answer?
You talking about 6?
Yeah, number 6. Yeah. What's the answer?
Oh,
1 3, right? So this is the first group, right, from the table. This is that, so it's 3, right? So 3 comes first, right? Then we have 1, just 1, right? So um, so when you write this, let me go to this one and quickly show you guys that. So we have basically um, come on, all right. So we have um, 1 0 0 1 1, right? So this is the first group, right? This is 13, right? So next group also should be 4 groups of binary bits. So you can actually imagine or write 3 more to make it a group, okay? Right? That's totally fine because the zeros on the left side after your numbers is irrelevant, right? So this is the other group, a group of 4. This is what? This is sorry. This is 3. Sorry, I take it back, guys. Sorry about that. This is 1. Yeah. So the answer is actually 1 3. Okay. All right. In what base? 16. Yeah. Okay. All right. Okay. So let's do this one real quick now. What is the answer to this one?
Uh,
7 is so. Um, so let's start off with 7, right? 7 is um, 0 1 1 1, right? So then we have to go right here, another 7, right? 0 1 1 1, and go again to the front. So now we have 0, right? So you're gonna write 4 zeros. Yes, okay. So and there's one more 0, right? So you're gonna write 4 more zeros. All right. See that this 1 0 in hex is 4 zeros in binary, right? So that's what I did. Okay. And now we have f. F is 1 1 1 1. So we have one more, right? So we're gonna go to the front again and write 1 1 1. Yeah, I think this is correct. Yep. Okay. All right. All right. So 12 o'clock. Let's get our break. Be here around 12:06. Okay. He's calmer today. Is it he or she?
It's a girl.
Oh, okay.
Yeah.
She's calmer today.
Yeah.
The other day.
Gotta get
Yeah.
the feel of the class because you rather see now you see.
Yeah,
both of
yeah.
them. I gotta make sure everybody's all right with it.
No, that's fine. It's
Yeah.
fine. Yeah.
She really likes people.
Yeah, it
Yeah.
looks like, yeah.
Yeah.
I mean, if when we smile and then she recognized that and then
Yeah, it's
how,
instantly.
yeah, yeah.
She,
She knows that I'm talking about her.
yeah, exactly.
Yeah.
Yeah, since we behaved, focus him. No, you cannot. Fair play against that. No, you cannot. No, you cannot.
Sorry? Yeah, yeah.
Oh wow.
I got one.
Kind of cute.
Thanks. I got one because when I talk right here, it's not gonna record, right? So now it is, yeah. But and the thing is now it's going to record private conversation with the student as well. So I have to be careful. Yeah.
submission because I did the image, but I'm not seeing the insert.
Oh, all right here. Wow, let's just.
I should because I did it. I took the image on my phone.
Yeah, let me see. Maybe it's at the top. No, okay.
So I hit a reply.
Okay. Oh, let's click on that. Yeah.
This one?
No. Okay.
Yeah.
That's weird.
Should it,
No, and this. No, that's also not that. Wow, that's really weird. I mean, it should show, right?
it should, yeah.
Whoa. Wow. Okay.
Oh, shit.
Yeah. So let's take a look again.
Okay.
Yeah. I mean, you're right. This is. There's no other control. No.
Could it be for? Oh no.
No. Nothing there. Shall we check with another student? Maybe it's sometimes I have seen that they it's a bug probably in mobile bug in there that they don't show the the
Yeah.
yeah
I seen it on the module on the when you can I can do it on here.
yeah
I
you
couldn't-
can
but I-
we
but
can
I had
see
the
it
image
there
on the-
but
on the
yeah
image
I
on the
think
phone.
that's okay. So can I do this? Let me
Yeah.
do that. See if that makes any okay. Yeah, not in there as well. Wow, that's good to know though, because
Yeah.
students use mobile app too, right?
Yeah.
Oh, there you go.
Where is it?
You can scroll it.
Oh.
So you can scroll it this way. I guess
Okay.
we can. I think we can. I think this is the button. Let's see that image button.
Let me see.
Click on that.
This one.
Yeah. There you go. Upload.
Okay.
Yeah. Embed image. Yes. Yep.
Okay. What?
Cancel. So
So hit the image, right?
yeah. Upload or embed image. What is this? It's already like it said. Oh, yeah. So you will go to the next image. I don't know.
Yeah.
It's there actually. You can
Okay.
take some time to understand.
Oh, shit.
Yeah.
Okay, I'll try to.
All right.
Cause I submitted the image.
Oh, okay. You can always use the computer if it's easier. Yeah.
Okay.
Hi.
image, or you said never hit that?
No, no, attach. Just going to attach. Yeah. So
Let's see. Okay, because it's not.
it's gonna attach. I think if you click attach.
Okay, this was it,
Let's see.
and then
No, it's gonna just only attach. Like people will see only the file name.
yeah, that's right.
Yeah.
So
So let's go on. Maybe the other one. That one.
no, it's
No,
Canvas
Canvas
Studio.
Studio. Yeah. So let's click on that again.
Yeah, I don't know what.
Yeah, it's okay. You can go. I think. No, that's not that. Why it's actually it's looks like already there, right? Cancel it.
So I don't have the image there yet. Cause
So okay. See if we can scroll. Oh, there you go. Now it can. No, it's studio again, right? You don't need that. Yeah, this is the one. Yeah. Let's see. See if we can scroll this. No.
yeah, there's another.
Still like. Oh, it's a fatal error. See that? Maybe it's your iPhone. I don't know. Maybe blocking it. So
Oh,
see that it's an error.
okay.
So it should be maybe it's you can read what is happening.
Okay,
Yeah,
okay.
looks like that.
Alright.
Yeah.
I just wanna make
Yeah.
sure. Okay.
Okay. Do we have everyone? Oh, okay. So I think. All right. Let's watch our video, guys. Okay. So. Yeah, this one. All right, guys. I just published it. It's in module 2. Okay. You guys can review refresh the module view. Okay. So this is the one. It's in module 2. It's good. It's a good video on how computer memory works. We already kind of learned this one, but it's good overall summary. Okay. All right. So let's watch.
In many ways, our memories
Give me
make
one
us who
second,
we
guys,
are,
sorry.
helping us
Sound is
remember our
not clear.
past.
Yeah, because I removed this one, so I'm gonna.
In many ways, our memories make us who we are, helping us remember our past, learn and retain skills, and plan for the future. And for the computers that often act as extensions of ourselves, memory plays much the same role. Whether it's a 2-hour movie, a 2-word text file, or the instructions for opening either, everything in a computer's memory takes the form of basic units called bits, or binary digits. Each of these is stored in a memory cell that can switch between 2 states for 2 possible values, 0 and 1. Files and programs consist of millions of these bits, all processed in the Central Processing Unit, or CPU, that acts as the computer's brain. And as the number of bits needing to be processed grows exponentially, Computer designers face a constant struggle between size, cost, and speed. Like us, computers have short-term memory for immediate tasks and long-term memory for more permanent storage. When you run a program, your operating system allocates area within the short-term memory for performing those instructions. For example, when you press a key in a word processor, the CPU will access one of these locations to retrieve bits of data. It could also modify them or create new ones. The time this takes is known as the memory's latency. And because program instructions must be processed quickly and continuously, all locations within the short-term memory can be accessed in any order, hence the name random access memory. The most common type of RAM is dynamic RAM, or DRAM. There, each memory cell consists of a tiny transistor and a capacitor that store electrical charges, a 0 when there's no charge, or a 1 when charged. Such memory is called dynamic because it only holds charges briefly before they leak away, requiring periodic recharging to retain data. But even its low latency of 100 nanoseconds is too long for modern CPUs. So there's also a small, high-speed internal memory cache made from static RAM. That's usually made up of 6 interlocked transistors, which don't need refreshing. SRAM is the fastest memory in a computer system, but also the most expensive, and takes up 3 times more space than DRAM. But RAM and cache can only hold data as long as they're powered. For data to remain once the device is turned off, it must be transferred into a long-term storage device, which comes in 3 major types. In magnetic storage, which is the cheapest, data is stored as a magnetic pattern on a spinning disk coated with magnetic film. But because the disk must rotate to where the data is located in order to be read, the latency for such drives is 100,000 times slower than that of DRAM. On the other hand, optical-based storage like DVD and Blu-ray also uses spinning disks, but with a reflective coating. Bits are encoded as light and dark spots using a dye that can be read by a laser. While optical storage media are cheap and removable, they have even slower latencies than magnetic storage and lower capacity as well. Finally, the newest and fastest types of long-term storage are solid-state drives, like flash sticks. These have no moving parts, instead using floating gate transistors that store bits by trapping or removing electrical charges within their specially designed internal structures. So how reliable are these billions of bits? We tend to think of computer memory as stable and permanent, but it actually degrades fairly quickly. The heat generated from a device and its environment will eventually demagnetize hard drives, degrade the dye in optical media, and cause charge leakage in floating gates. Solid-state drives also have an additional weakness. Repeatedly writing to floating gate transistors corrodes them, eventually rendering them useless. With data on most current storage media having less than a 10-year life expectancy, scientists are working to exploit the physical properties of materials down to the quantum level in the hopes of making memory devices faster, smaller, and more durable. For now, immortality remains out of reach for humans and computers alike.